Got it. So shall we start, Alexey?
Yep.
Very good. So it's my great pleasure to introduce Professor Alexey Onatskiy. Professor Alexey Onatskiy received his PhD from Harvard University in 2001, and he has worked at Columbia University and is currently in Cambridge University since 2010. He is a renowned expert on high-dimensional statistics and econometrics, as well as random matrix theory. And it's a great pleasure and honor to have him here with us today. Alexey, the floor is yours. Please go ahead.
Thank you very much, Majid. Thank you, everybody, for attending. And I thank organizers of this event. It's a very good one. So let me share my screen and just maximize the screen. Okay, so my talk today will be about a work in progress. The title of this work is Uniform Asymptotics for Weak and Strong Factors. So let me explain what it is about. So we will be considering a very simple factor model and principal components estimates of this factor model. So suppose that you have T by n data. T is maybe number of time periods that this data has, and n is cross-sectional dimension. Both T and n are large, and this data has a latent factor structure. So the latent factor structure is represented by this low-rank matrix F times lambda prime, where F is a matrix of factors, and lambda is a matrix of loadings of these factors. And there is another component in the structure called epsilon, which is a matrix of idiosyncratic terms. And usually people assume that the factors are relatively strong in the sense that their cumulative explanatory power is growing with the cross-sectional dimension. Technically, this is reflected in the following requirement. Lambda prime lambda, it's basically the sum of squared loadings divided by cross-sectional dimension taken into some power, alpha, converges to some positive definite matrix, sigma. And the asymptotics of the principal components estimator of factor and loading is usually tied up to the value of this lambda, to the speed with which the explanatory power factor, explanatory power of the factor is growing with the cross-sectional dimension. So let me remind you that the principal components estimator of factor will be simply proportional to the eigenvectors of the sample covariance matrix of this data. So you just take X, multiply by X transpose, and look at the eigenvectors, and this will be spanning the same space as your principal components estimator of the factors. So we are interested in designing asymptotics of this estimator, which will not be tied up to alpha. So let me draw this this line where parameter alpha leaves. And so far, there were a lot of work on the asymptotics of principal components estimator, but they were specific for each of the points on this line. For example, the original work on high-dimensional factor models was focused on so-called strong factors, where alpha is equal to 1, and the explanatory power of factors is proportional to the cross-sectional size. Later, people realized that actually the requirement of the proportionality of the strength of the factor to the cross-sectional dimension is not very well linked to what data is saying, because in many applications, for example, in financial or macroeconomic applications, the explanatory power of estimated factors is very quickly decaying with the number of factors. For example, maybe first factors explain quite a bit of variance, but second, third factors, they explain an already very small proportion of the variance of data typically. So people try to capture this in considering different asymptotic regime with lower alpha. So many people, for example, consider alpha in between 1/2 and 1, and some literature is calling these factors weak or semi-strong factors. There is also literature on extremely weak factors, and I contributed to that literature where alpha is assumed to be 0. I haven't seen much results on alpha in between 0 and 1/2. So, but today I'm going to propose something which works uniformly in this region for alpha from 0 to 1, covering this interval as well. And so the advantages of this uniform approach are as follows. So first of all, estimating alpha is notoriously difficult, if possible at all. So using this uniform asymptotics, you do not need to make the step of estimating alpha, or you don't even need to take a stand on the value of alpha. If you just want to postulate alpha, you don't need to do this. Well, of course, asymptotic formulas that I'm going to derive will not be alpha specific. And this asymptotic is also good in the sense that it will work independently on whether factors are strong or weak or extremely weak. So this will be just the same asymptotics, which is extremely convenient. The results that I will get will also clarify what happens in this region where very few papers, if any, worked with when alpha is in between 0 and 1/2. And also, I will make very weak assumptions about the relative rate of growth of cross-sectional and temporal dimension of the data to infinity. So we will only need the following thing, that T will be either dominating or of the same order of magnitude as n taken into power 1 minus 2 alpha. So so this is actually extremely weak assumption on the relative rate of growth, and it weakens existing assumptions quite considerably. The existing assumptions that I know usually require that T is dominating n taken into power 1 minus alpha, but here we're allowing 1 minus 2 alpha. And finally, I think that the approach that I will propose emphasizes important technical issues. It emphasizes the central role of the resolvent of the sample covariance matrix in all this analysis. And this emphasis allows to focus on important things and maybe to kind of provide a more systematic approach to all kind of analysis of principal components estimators. So the presentation plan for the rest of my talk is as follows. First of all, I will be considering the simplest possible illustrative framework. The goal will be just to understand this approach to uniform asymptotics, so I'm not going to consider any complicated situations at all. So then I will talk a little bit about standard approach to asymptotics of principal components estimator, our approach. I will describe some uniform asymptotics results. Probably I will not have time to go deeply into the toolbox that I'm going to use, and I will just summarize future research directions. So let me start from the simplest illustrative framework. In the simplest framework, I will have just one factor. So F is a vector here, and moreover, I will assume that this factor is Gaussian and has identity variance covariance matrix. Also, I will assume that this factor is independent from idiosyncratic terms, which are themselves Gaussian with mean zero and unit variance. So what will be flexible in this approach? The flexible will be the strength of the factor. The strength of the factor is usually measured by this squared sum of loadings, of sum of squared loadings, lambda prime lambda. And remember, I'm assuming there is only one factor, so lambda is a vector here. So this is literally the sum of squared loadings. And I will denote this strength of the factor as this lowercase n. I will not need really in my uniform asymptotic approach to specify any particular form for this lowercase n. But in the standard approach, usually people think that the strength of the factor is proportional to some power of the cross-sectional dimension n. So I'm putting this in red because this parameter n will appear again and again later in my discussion. Now, I will assume for now completely arbitrary relative rate of growth of n and t. The only thing that I will assume is that the rate of growth is polynomial. So, for example, n cannot logarithmically grow, but t polynomially grow. I want logarithm of n being like asymptotically of the same kind of order of magnitude as logarithm of t. So, but this is extremely weak assumption on the relative rate of growth of n and t. Okay, given this very simple approach, so let me very briefly describe in very, very general terms the standard approach to asymptotics of principal components estimator. So principal components estimator of the factor is nothing else as square root of t, the dimension, right, the temporal dimension, multiplied by the principal eigenvector of this sample covariance object, x times x prime. And usually in the standard approach, you assume that the systematic part of the data, which corresponds to the factors, is much bigger than idiosyncratic part of the data, in the sense that f lambda prime is dominating by norm, the norm of the epsilon. Well, this requirement assumes that alpha, which governs the strength of the factor, is greater than 0, and actually the capital T dominates n into power 1 minus alpha. So remember, on one of the first slides, I told you that my results will hold for T of the same order of magnitude or dominating n taken into power 1 minus 2 alpha, but the standard approach would require that stronger requirement. Now, well, with all these requirements, the standard approach usually is based on the perturbation theory to compare the principal components estimate of f to the value of f itself. So very roughly, how does it work? So we are looking at the sample covariance matrix, suitably normalized, and suitable normalization will be to divide by t and by strength of the factor. Then on the right-hand side, you will have the following things. So you will have f lambda prime lambda f prime divided by t, and I'm putting this n in the numerator because remember I defined n as lambda prime lambda, so this bracket is just 1. So overall, this appropriately normalized simple covariance matrix is just equal to f prime divided by t plus something which is small because it's related to the idiosyncratic terms. Now, principal components estimator is the eigenvector of this, okay, and factor itself is the eigenvector of this matrix, and the left-hand side can be viewed as a small perturbation of the right-hand side. Therefore, perturbation theory tells us that the eigenvector of the left-hand side should be small perturbation of the eigenvector of this first term on the right-hand side. And that's the basis of all this standard approach to asymptotics of factor analysis, because you simply need to analyze what is this small, how much this f hat is the perturbed version of f. So let me digress a little bit into perturbation theory and just describe to you the perturbation theory in a nutshell. So a lot of perturbation theory is related just to perturbation of matrices. And so like there is a book-long treatment of perturbation theory, which I particularly like. It's by Kato, perturbation of linear operators. And the framework of that perturbation theory is as follows. You have some matrix A, which is perturbed version of another matrix A0. And then most of the perturbation theory is based on the so-called von Neumann expansion of the resultant. So what is resultant? You take the matrix, subtract the complex Z, variable Z multiplied by the identity matrix from it, and take inverse. And this object is called resultant R. And it turns out that this resultant R can be very easily related to the resultant of the A0 matrix, which I call R0. So there is this algebraic identity that R is equal to R0 times identity plus this small thing multiplied by R0 taken into power -1. And this second multiplier here looks like a sum of geometric progression, really, only with matrices, right? So I can expand it into power series of small, and I will get this expansion, R0 minus R0 times small times R0 plus R0 times small times R0 squared, etc., etc. So this is called von Neumann's expansion for the resultant. It turns out that all objects are related to the spectral analysis, such as eigenvectors, projections on eigenvectors, eigenvalues, can be related to the resultant very easily. So for example, if you are looking at some particular eigenprojection, let's say P for A, so this eigenprojection on, let's say, particular eigenvector can be expressed through the resultant. So here is his expression. This looks a little bit scary for those who forgot the complex analysis, but it's basically an integral of the resultant, which is taken over the contour, encircling the particular eigenvalue corresponding to the eigenvector that you are interested in. So, and this representation of the eigenprojection and the von Neumann series imply the similar series for the eigenprojection. And then you can work with this series to say all kind of things about how eigenvector of your perturbed matrix is related to the eigenvector of your unperturbed matrix. Okay. So, so let me explain why is this important for factor models. And for this, I will provide you a dictionary between this perturbation theory and factor model. So in perturbation theory, there are these two matrices, A, which is perturbed version of A0. So for factor models, what is that? A would be the simple covariance matrix of the data, properly normalized. And A0 would be just the simple covariance matrix of factor itself, right? So simple covariance matrix XX prime is a perturbed version of this factor simple covariance matrix. Now, what is small? Small in perturbation theory would be in factor models, well, relatively small. It's should consider the squared norm of epsilon and divide by squared norm of the systematic part of the data. And this is what in perturbation theory would be called small. I can express this in terms of cross-sectional and temporal dimension as follows, or if you introduce this notation, C is literally equal to the ratio of the temporal dimension to cross-sectional dimension of your data, then you can express this in terms of C, and this formula will become important later on when I will make some simplifying assumptions. So just put it here because if I, for example, assume that C is fixed, which I will assume just for a couple of slides, but then I will relax this assumption again. But if I assume that C is fixed, then what is small? Small is basically kind of constant divided by n, where n is the strength of the factor. So small in perturbation theory would be reciprocal of the strength of the factor. Okay. Now, what is this eigenprojection? Eigenprojection P0 will be simply the true factor multiplied by its transpose divided by norm squared. Eigenprojection for the A in perturbation theory for factor models, this is projection on the principal component's estimate of the factor. So it's the same thing as this, but with hats on it. And then you can also consider like interesting combination of these things. For example, you can look at the trace of the product of P and P0, and this will correspond for the factors to the cosine squared of the angle between the principal components estimator and the true factor. And usually you would say that if this rho squared converges to 1, then we consistently estimate the factor space. And while there is, of course, a lot of focus on consistency and the estimation of factor space. So we can look at this rho squared and analyze its asymptotic behavior, but it's really just related to the behavior of the trace of product of P and P0. So we can use perturbation theory for that. Okay, so now let me talk a little bit about asymptotics of R squared in the standard framework. And for simplicity, again, just for simplicity for next few slides, and then I will relax this, I will assume that C is fixed. C, remember, is this ratio of the temporal to cross-sectional dimension. Then small is just the reciprocal of the strength of the factor. And for this rho squared object, which is, remember, related to either consistency or inconsistency of the factor space estimate, I will have this, the series in the inverse power of the factor strength. And so looking at this series, if I want to analyze the asymptotics of R squared, this reduces to analyze this asymptotic of the coefficients in this series. Turns out that you can quite easily prove that each of these traces converges in probability to some particular constants. Let me call them mu j. And if you centralize these traces by mu j and then multiply by square root of t, this object will converge in distribution to normal with mean 0 and some particular variance is sigma squared j. Well, it turns out that this behavior, this asymptotic behavior of coefficients, implies that the asymptotics for R squared will be different in different regimes of relative rates of divergence of n and t. So this perturbation-based asymptotics analysis calls for different centering regimes depending on the relative rates of divergence of n and t. So let me explain what's going on. So, so I have a series for rho squared, right? But I want somehow to use this series, it's my previous slide, and this results on the asymptotics of each particular term to derive the asymptotics of rho squared. So obviously, well, the first step probably would be just to take rho squared and subtract 1 from both sides, and then to multiply by n. Okay, so rho squared minus 1 multiplied by n will be basically this term plus something smaller. And that's what I have here. Rho squared minus 1 multiplied by n, and then I'm centering by mu1 multiplied by square root of t, and I'm getting something which is here behaves asymptotically normally, and I will have the rest of the terms hopefully small. But unfortunately, the rest of the term may not be small. Look at the second term. The second term here depends on square root of t divided by n. And of course, this term does not converge to 0 if alpha is less than or equal to 1/2. Because if alpha is less than or equal to 1/2, then the denominator here will not be dominating the numerator. And therefore, the second term will become also important for the asymptotics. And that's basically the reason why you don't have much literature, you don't have any basically literature on the asymptotics of the principal components estimated with alpha less than 1/2. Because it calls for the second order asymptotic analysis using this perturbation theory. And people usually just use first order asymptotic analysis. Okay. But this is not all, because you can take into account the second order term and, well, simply center by mu2 divided by n, and then you would get this second order term centered correctly, and actually the numerator here will converge to normal, denominator will diverge, so overall this second term will become not important. However, the third term will become important now, because well, it only converges if alpha is greater than 1/4, but if alpha is less than 1/4, this term will explode. So there will be another term to take into account. So overall, we can formulate the following theory. Suppose that the C, the ratio of temporal to cross-sectional part, is fixed. And then, depending on the regime of alpha, where it is relative to 1 and 0, so if it is in this particular interval, then I will need to use different centering of rho squared, and then multiplying it by square root of t and divided by sigma 1, this object will converge in distribution to standard normal. And it turns out that this centering constants are easy to compute for j equal to 1, but for j greater than 1, this becomes quite painful to compute them, but it's still possible. But later on, you will see general formulas for this mu1 and sigmas that will follow from the uniform asymptotics that I will propose. But if you just do it directly by brute force, then this will become not as easy to do. Okay, so let me switch to the alternative approach. And the idea for the alternative approach would be not to try to link the resultant of x prime to the resultant of the systematic part, as the perturbation theory suggests, but instead link the resultant of x prime to the resultant of the idiosyncratic part, epsilon prime, and then use the Sherman-Morrison formula to exploit this link. Well, basically, this will put the principal components analysis into the M estimation framework, as you will see, and we will use the standard tricks of M estimation approach to well, derive asymptotics of the principal components estimator. So let me say a few more words about how you can link the resultant of x prime to the resultant of epsilon prime via the Sherman-Morrison formula. But before I do that, it's just again summary: standard approach versus our approach. In the standard approach, you're considering this decomposition of the simple covariance matrix in the systematic part and something small. Then use perturbation theory to link the principal components estimator to the actual factor. In our approach, we will consider like the same decomposition, but we will treat this matrix as simply low rank matrix. And we will not look at this small as some black box, but we will just say that this small is epsilon prime. And then we will use Sherman-Morrison formula to link eigenvectors of this object with epsilon prime and the low rank matrix. There will be some like function linking them. And then we are going to exploit this equality to derive properties of f hat in the same way as the usual M estimation or Z estimation framework uses this kind of identities to describe properties of your estimators, which usually this function will relate some simple sample quantities to population quantities, and then we'll exploit the this identity to figure out asymptotics of the sample quantities. So that's exactly the same approach here. Okay, Sherman-Morrison formula is linking the resultant of matrix A perturbed by low rank matrix to the resultant of A itself. Here, instead of Z, I'm using lambda, but on previous slides I was using Z, so here it just stands for Z, and that's the formula. What it implies the following thing. First, for eigenvalue of A plus ff prime, where the script f can be anything of small rank, and actually here in this formula is rank 1. So the eigenvalue turns out to be something which makes this denominator equal to 0. So for eigenvalue of A plus ff prime, it must satisfy this formula. And also you can figure out some constraints on the eigenvectors. The eigenvectors of A plus ff prime must satisfy this formula. So, and these two formulas will be enough for me to analyze the asymptotics of both eigenvalues and eigenvectors in the factor model framework. So let me provide you some dictionary between this factor models and Sherman-Morrison formula. But before I'm doing this, I will do slight simplification of the framework, further simplification. Remember, everything is Gaussian in my framework. So actually, because the Gaussian distribution is invariant with respect to rotation, I can, without loss of generality, consider lambda, remember this factor loadings, completely concentrated on the first coefficient. So first coefficient will be square root of n, but the rest coefficients will be zeros. And this will not change at all any asymptotic results on the factors of factor loadings, because the Gaussian distribution is invariant with respect to rotation. Also, I will partition my matrix of idiosyncratic terms into the first row and the rest. And this first row will be something which will be mixed with the factor, because factor is loads on the first term, but this rest of the columns of the matrix will not be mixed with the factors at all. And so I will be working, instead of epsilon prime, with UU prime. Okay, so UU prime basically is the simple covariance matrix of idiosyncratic terms here. Okay, so let me now come to the dictionary. Sherman-Morrison describes this A plus FF prime, the properties of the resultant of this A plus FF prime. So what is this A plus FF prime? In terms of factor model, this is simple covariance matrix of our data. So what is A? A now will be the simple covariance matrix of my idiosyncratic terms. And it is perturbed by what? What is this F? F will be some linear combination of the factor and the first column of the matrix of idiosyncratic terms. Okay. So what is this resultant of the unperturbed matrix? Well, this is resultant of the simple covariance matrix of the idiosyncratic terms. What is V, the eigenvector of this thing? It's my simple covariance, well, the eigenvector, right? So it's principal components estimator of factor scaled by square root of t. What is lambda? Principal eigenvalue of the simple covariance matrix. Okay. So we will be interested in the asymptotic properties of this and of the eigenvalue. So how do we get the asymptotic properties of eigenvalue? Remember, we have an equation for this eigenvalue. So from Sherman-Morrison formula, the eigenvalue should satisfy this, this equation. If we normalize this F things so that they become the standard normals, then we can reformulate this, this equation in this form. So there will be standard normal vector prime multiplied by some resultant of the idiosyncratic terms. Remember, sample covariance matrix of idiosyncratic terms. Multiply again by this standard normal is equal to some constant related to the strength of the factor. As factor grows, the strength grows, this constant becomes smaller and smaller. So then we simply will use usual M estimation technique to say what are asymptotic properties of the solution of this equation. So really, so what is this technique? We need to look at the fluctuations of the left-hand side. So this left-hand side is concentrating around the trace of this resultant. So I'm putting it in the black line here. And there are some Gaussian fluctuations of this quadratic form around this trace. And then we can figure out the fluctuations of the solution of the equation using just information about fluctuations of the quadratic form. So the most difficult part in this analysis will be to get exactly this line here, because this line itself will be random, because it's the trace of the resultant of the sample covariance matrix of idiosyncratic terms. And sample covariance matrix of idiosyncratic terms is random, so this trace is also random. So this line itself is random, so I must be very careful with how these lines behave, and I will be using random matrix theory to figure out this behavior. Okay, so using this framework, I'm getting this this theorem. Well, suppose that n and t go to infinity at arbitrary rates, but I will require something about the strength of the factors, and this requirement is really very weak. So all that you need to know right now that it actually allows for alpha to be anywhere in between 0 and 1, and for alpha equal to 0 as well. Okay, and then if you take lambda and subtract this deterministic term here, then multiply by this factor, this converges in distribution to standard normal independently of the strength of the factors. It can be weak, extremely weak, strong, whatever, you will get this. So you may ask how come, because I've got different centering regimes for factor for the in the previous analysis. Well, it's actually because of the following thing. So let me formulate similar theorem for rho squared, the object for which I had these different centering regimes. So there is similar theorem for rho squared. It's uniform asymptotics for rho squared with some particular centering here. And the centering here is not different for different alphas, because actually it can be simply decomposed into the series of negative powers of n, and the coefficients of this series will be those different centerings that are required under the standard approach. So in the standard approach, these coefficients were different for different alpha, but in my approach, this coefficient will be simply the Taylor coefficients in the expansion of this centering into negative powers of n. Okay, but then you have uniform asymptotics. And well, I have some Monte Carlo showing that uniform asymptotics works really well for any strength of the factors. And so the toolbox, I don't have time to describe that, but so I will just jump directly to the directions for future research. So I right now, considering extremely simple approach with everything Gaussian and things like that, But you can consider general idiosyncratic terms with quite complicated dependence between them. You will need some more results from random matrix theory to derive the uniform asymptotics. So then you can consider non-Gaussian data as well, and very powerful methods based on this Lindeberg swapping techniques were developed recently to go from Gaussian to non-Gaussian data. Also, I would like to extend the analysis for alpha from interval 0 to 1 to even to negative alphas, because I want just to completely span all possibilities there. And also consider more than one factors. So, but this is for future research. And this project just describes the possibilities for this uniform asymptotics using really, really very basic framework. And I'm done with presentation. Thank you very much for your attention.
Thank you so much, Alexey. That was wonderful. So we have time for questions. So I have a question from Simone. So the question is, there are two ways to get factors. Take alpha is equal to 0. You could either have drifting sequences for the loadings, lambda proportional to 1 over square root of n, or have just a mixed number, for example, a single one, of loadings unequal to 0. I couldn't quite figure out if the second scenario, weakness through sparsity, is ruled out in your model.
The second scenario definitely will result in weaker factors than just very strong factors. It is not ruled out from this analysis, and you can apply this analysis to sparse situation. However, you will be losing something by doing that, because you will not be taking into account sparsity at all. This uniform asymptotics will work independently whether you consider sparse situation or not sparse situation. So you will be losing something if you actually have information about the nature of the sparsity. Thank you for this question. I know your own work on the sparsity, and that goes in the very right direction, especially in the case when you can say something about the sparsity. It will probably provide a more efficient, potentially more efficient estimates of everything, because you're exploiting this sparsity. In this approach, there is no exploitation of sparsity at all. It will work whatever, but probably will provide less efficient result.
Very good. Thank you, Alexey. So I don't see a question. I have my own question, if I'm allowed to ask. So the trace of the resolvent, that looks like a Stieltjes transform, right? Is it?
Yeah.
Okay, so
that's a Stieltjes transform, and people in random matrix literature derive a lot of results from the properties of Stieltjes transform. So the recent results on the properties of Stieltjes transform were strengthened tremendously relative to what was available, let's say, 10 years ago or 5 years ago, because people started to consider asymptotics of Stieltjes transform on a finer and finer scales. So they not just look at the asymptotics just of Stieltjes transform, but ask at, so what will happen if this Z in the Stieltjes transform, remember in the resultant there is this complex variable, approaches to real line to these points of singularities of the Stieltjes transform. And actually this analysis becomes very important for uniform asymptotics that I'm proposing, because it allows me to get very, very accurate formulas on the Stieltjes transform, which are needed to get the M estimation framework work, even in the situation when the constant is very close to 0 and the line with which I intersect this constant is almost flat there. So I need really, really very precise control of those fluctuations, and that is obtained from the Stieltjes transform analysis.
I see. Thank you, Alexey. So I'm checking the chat, And there are no more questions. So I think we can then close the session. And let me thank Alexey so much for his wonderful presentation. Everything was crystal clear. Thank you. It was wonderful. And,
thank you very much for everybody who attended. Thank you for questions.
Very good. Take care, everybody. See you in the next sessions. Take care.
Bye-bye.
Bye-bye.